Welcome everyone. This is the second part of the fifth lecture. I'm going to show you today the Lukas Kanade tracker. This goes back to a paper by Bruce Lukas and Takeo Kanade, published in 1981, which is my birth year. You will find many different references to that tracker. This is the, let me just switch to my pointer. This is the main or the first paper, but has been augmented or extended by different people and in different publications. For example, OpenCV implemented that pyramidal implementation of that tracker. I would suggest you reading this paper here by Matthew Baker, which gives you a nice introduction and history of that tracker. The idea behind the Lukas Kanade tracker now is let's consider this gradient, right? So it's nice and smooth and linear. So at this point, we have a gradient that is a vector pointing upwards. Now, if we look at only one point, and I'll give you just a little bit more just to see what brightness that patch has, and then we'll move that object by a certain amount of pixels. We see that that point got darker. So if I asked you, how and where did that object move, what would you say? So I hope your answer was the object moved leftwards, so into the direction the gradient pointed. What if the pixel got brighter? Again, we would have said and expected that the object moved rightwards, right? So our point that we observe, that one here, got brighter, right? So comparing two brightnesses at time point t and time point t plus 1 gives us an expectation of the object's movements with respect to its gradient. And that's the entire idea here. And now let's look at the math. So in the simplest case, in a one-dimensional scenario, we have our spatial dimension x, could be one row in an image. And here on the y-axis, we have the image brightness, okay? So our 8-bit values. At time point t, the image could, be looking like that, and then that object may have moved from one frame to the other to the left, and we call that function here it plus 1. Yeah? And now, since the object didn't change, was just shifted, we can have this simple equation here. So the function value of the shifted version at location x is just the function value of the previous version at a shifted location. Yeah? And now let's try to formalize what we saw on the slide with this gradient, with this black and white gradient. So the spatial derivative here, yeah. So it dash at point x can be approximated, and that is what you should have seen in school already, by the difference of the same function at different but neighboring places, and they are h units apart, divided by h, right? So this is what we typically do, and the derivative is defined as the limit of this this term here. So h goes to 0, but for now let's keep h above 0. So and then what we'll do is we just use what we saw on the previous slide. Remember that it at the shifted location is the it plus 1 function at x. Okay, and so we'll replace that. And so what we'll have is we look at the image brightness difference at the same point and divide by h, and we will have an approximation of our image gradient here at this point. Yeah? And now what we could just do, we multiply by h and divide by that gradient, and we have an approximation of how much the object moved. Yeah. So again, let's summarize, because this is really important, and this will come up on every slide from here on. The difference of the brightness at the same point between frames. Yeah, so that's the temporal derivative at a certain point, divided by the image gradient, allows us to have an estimation of, or an approximation of, how much the object moved. Let's have a look at a couple of examples, numerical examples, so we can get a feeling of how that works. So again, this is what we have seen on the previous slide, and we'll use linear functions, and that approximation becomes an equation. And let's see how that works. So we'll leave out those edge cases where we have two parallel lines, either vertically because the gradient isn't defined, and also the ones that are parallel, like horizontally, because then division by 0 isn't defined. Yeah? But let's have a look at these versions here. So we have, let's say, one unit here are like one gray and one white box, and so those two functions are shifted by 1, right? So it is this yellow function, and it plus 1 is the blue function. And you see the slope of both functions is 1. So if I go right 1 unit, I have to go 1 unit up to hit that line again. So that's the slope, which is that part here. And so if I choose any x, let's say this, and if I look how much the brightness is or differs, I see that the difference is 1 divided by 1 gives us an h of 1. That's correct. Let's see how that plays out if I have different slopes. So again, at a certain x, I can compare the two function values, which here have a difference of 0.5, and the slope also is 0.5. So again, if I divide these two values, I get a 1. And that works also with smaller slopes or higher slopes. Okay, that makes sense. Now let's move to 2D. First, let's consider again a brightness change that we call C for change between frames at a certain position, right? So let's say at that point here, I zoomed in a little bit. First was a little brighter, and now it got darker. And our gradient that we call G here is just the vector of our image gradients that we call I subscript x and I subscript y at that location x. Okay. The object motion, let's call it v, is also a vector in x and y. Okay. So what are possible object motion vectors v that could produce c? So the brightness change. Sure. So again, that was the example from one of those first slides. What if that dot here got darker, or that patch got darker? Well, we said we probably expect the object to have moved leftwards. Now, what if the object did not move exactly into the direction of the gradient, but maybe in that blue direction here? To produce that exact brightness change C, we kind of directly know how much it would have to move, because because of that linear gradient that we have here, that brightness change is the same when the amount of motion into the gradient direction was exactly c. And how do we get to that property? Before we answer that, another example. So even a motion direction that is much farther away from the gradient direction then needs to be much longer to have that kind of component into the gradient direction. And so what I want you to understand is that any motion v whose projection on the gradient vector g is equal to c is a valid motion vector, right? Is a valid explanation for that single brightness change c. And obviously we touch again the dot product. That is exactly what we do, right? So the unknown, that's what we seek, right? That's what we want to solve for. The vector of the motion v transpose g, the gradient at that point, needs to be approximately c. Okay, so in practice, we do have a window, right? Remember our Harris corners? We identified exactly those windows that have a bunch of gradient directions and not just one, or small gradients. So that example here, the dog's eye, that's one of those perfect key points that we think are perfectly to track. Well, but now we have different gradient directions. So how does this work, and how do we find the correct flow vector v? Well, the point here is that we not just have different gradient vectors, we also have, for these points in that window, different brightness changes. Yeah? So for example, if the dog moved leftwards, that point probably will get brighter and that dot will get darker. Yeah, so we have different information for these points in that window, and now we can have we can ask which of these flow vectors, so the object motion vector, agrees with all of these equations the best. And the standard way to approach this is to solve for v for many of these data points. So we collect first in a tall matrix A all those gradient vectors at all the points in the window. So x derivative of I at that location and the y derivative at that location, and then we collect all these points in that tall matrix. And B collects all the brightness changes at these points, at these respective points, right? So if we multiply V to A, we get exactly the previous set of equations. Now the thing is that due to noise and due to the underlying idea to be too simplistic for the 3D scene and all these things, the solution will probably only be an approximation, right? So there's no unique solution with zero error of this. So how do we solve then for V? So before I explain the way we approach this, first we have to add a little tweak here, which makes the solution more stable. We'll multiply a diagonal matrix W to A or to AV, which just represents Gaussian weighting. So the window that we have, you know, and the gradients in the matrix A are scaled, so weighted by by a number that is highest in the center of the window and falls off towards the periphery of the window. And the same will be done with the brightness changes that are collected in B. Now, so how do we solve such a system of equations such that the solution V is, or minimizes the errors between the solution and the vector B? So what we'll do is, so first of all, we cannot invert WA, that matrix, because it's very, very, very tall. It's we need to do something, and then what we do is we multiply that A transpose to this. So this is then a square matrix, and since we do that on the left side, we do that on the right side as well. So the equation is still holding. Now we then invert this and multiply that to the right side, and that part here is called the pseudo inverse. So that exists even for non-invertible A's, and if it's invertible, if A is invertible, the pseudo inverse is the inverse. So that produces our solution V. And if that was too fast for you, there is a lecture on this in I think in our machine learning course. I'll drop a link if that is true. Okay, so your task now is not to implement this, but to understand the math, understand the basic idea. There's an OpenCV implementation of Lukas Kanade, although it has, I think, a long list of tweaks that we haven't yet talked about, and we probably won't. But still, please play around, find limitations of this algorithm. So what kind of motion, camera-wise or object-wise, is it able to find, or is it able to discover, or in what kind of motion can't it discover? And so that shouldn't cost any more time, implementation time. It's just, to get a broad view of what we have talked about today. Okay, thanks so much. See you all next Wednesday. Ciao.